Alright guys, so for today's video, I'm going to be picking up from where we left off last, which is the reaction sheet. We just finished page, page 4. And today's video, I'm going to try to cover at least most of these reactions and maybe split up the last few in another video. But today, I will be covering all the reactions, the reaction sheet, even the ones that we have not done so far in class. So the first reaction that we're going to be doing is this reaction. So we've learned how to turn an alkyne, right, a terminal alkyne, into a strong nucleophile, aka or strong base, right? Very similar. It's a strong nucleophile in certain environments, strong base in others, right? If there's an acidic proton, it's going to be it's going to act as a base. If there's a electrophilic site and there aren't really many protons available to be abstracted, that the pKa is low enough to take, then it'll act as a nucleophile, right? So we've learned how to use this acetylide anion, right, that we form here using NaNH2, and we've learned how to use it as as SN2 and E2, and as a nucleophile in the substitution of carbonyls. All right, so now let's learn how to make them. So if you've learned this in class already, which you have, one way to make them, there's two ways, and they each create a different type of alkyne. There's only two, right? There's an internal alkyne and there's a terminal alkyne. So to make the terminal alkyne, the one that we use to make the acetylide anion, right? We can only make the acetylide anion from the terminal alkyne, and this is the terminal alkyne right here. It's highlighting everything, but this is the terminal alkyne, and the only way we can make it is using NaNH2 on degrees Celsius in good amount of yield, right? And an important second step is using H3O+. All right, and if I want to make an internal alkyne, I have to use KOH 200 degrees Celsius. So strong bases in extreme conditions, a lot of heat, and this is how we're going to force the triple bond to form. And the way that we do this, we use either vicinal or geminal dihalides. So usually dibromide, but vicinal is when the two bromines are one carbon away from each other, so they're not on the same carbon. And then geminal is when they're on the same carbon, like this, okay? And I can use any position. Any position will give me any one of these. So if I'm trying to form the terminal, I can use any one of these these vicinal or geminal bromines on these molecules to form the terminal one. The triple bond will move around all the way until it reaches the closest end, and I'll show you how that happens, okay? We'll learn how this mechanism works, just for the sake of understanding. And then if I have KOH, I'm going to form the closest internal triple bond. So if I was trying to form this one, I can either form it on the left side or the right side, doesn't matter. If I'm trying to form the one right here where the BRs are at the very end, I'll form it right over here, right? This is the closest internal triple bond. I cannot form it between this carbon right here and this carbon right here. It has to be between this carbon right here and this carbon right here, right? So just know the conditions. You can memorize it, right? You can simply just memorize, but I think it helps to see how it looks. So if we look at it, right? So let me take a quick picture of it. Right, and just put this over here. All right, I'm going to draw some sample molecules really quick, and then we'll look through the mechanisms, okay? All right, so I know she showed this in class, but it was like at the very end, so it was maybe a little bit hard to see what she was doing. Now, I'm going to use this molecule for both, showing you the NaNH2 and the KOH. They have the same mechanism, but they're slightly different in their nature and their chemical properties, right? So let's look at the NaNH2 one, because that's the more difficult one, right? How a triple bond can just move to one end or the other is a little bit weird, right? So normally, if I do this reaction, the first place that you always form the triple bond, if they're vicinal, is always in between the two bromines. So the carbons that have the two bromines on them, you're going to form a triple bond there first, right? Mechanistically. So this is just, we have a strong base, we have leaving groups, so we're just going to be doing E2 reactions, right? So I have NH2 minus, and this is going to come with a pair of its electrons, right? And I have a hydrogen over here, and I have a hydrogen over here. Okay, so I'm going to take one of these hydrogens, and I'm going to form a double bond, and I'm going to kick off this bromine. Okay, so let's draw that really quick. All right, so now I have this. So I took off this hydrogen, formed the double bond, and kicked off this bromine. And so now it just repeats again, right? So this is happening under extreme conditions. So these things help promote these reactions, right? And help promote the rearrangement and the continuous abstraction of protons. So help this progress, okay? So I took off this hydrogen down here. So, and now I'm left with the bromine over here. So now I still have a hydrogen over here. And so I have lots of these in concentration. Okay, so I have another one, and it's going to come, take off this hydrogen, add another bond, and kick off this bromine, right? Can keep doing this, and now I've maximized that triple bond, but I can keep doing this as long as I have another one of these leaving groups, okay? Alright, so now I have triple bond, but like we said that this is going to make it a terminal one, but I don't have the terminal right now. I was forced to make the internal one at first. So what happens really is that the conditions are so extreme, and I have such a strong base. NH2 is a strong base, so is KOH. But the thing you need to know is that NH2 is a stronger base than OH, right? So OH minus is a weaker base than N minus, right? It just makes sense because the electronegativity is less, right? So there's less stabilization. That negative charge is much more unstable. So this NH2 is more eager, more aggressive in trying to abstract protons from anywhere it can. So I have still extreme conditions. I have a lot of these bases that are still present. So what we're going to do is I'm going to look at the closest side, right? It doesn't have to be the closest side, but for sake of simplicity, I'm going to look at the closest side, and that's normally where we'll form the triple bond, right? You always want to form the, let's say we have NH2, we'll be forming on the closest terminal end, okay? So what we're going to do is I'm going to have another one of these, move the arrows this direction. So I have another NH2, okay? And what happens is I take a hydrogen from right here, okay, on the end that I want to move towards, right? So on the end that I want to move towards, I look at one of the hydrogens, and the NH2 is going to abstract one of those hydrogens, and it's going to form a carbanion on the carbon that it was attached to. So let's look at that. So I'm going to copy and paste this again, and we said we're going to form a carbanion, so I just have a pair of electrons here. So now I have a negative charge on a carbon, I have a triple bond, and what happens essentially is I'm going to resonate, right? So I'm going to resonate these in over here, and I'm going to push one of these bonds outwards, okay? So what we're going to get, right, let's look at that. So now I'm going to get this, okay? So I have this, and I'm missing the lone pairs, so the lone pair moved out over here, okay? So I have a negative charge over here now. Alright? So I have negative charge over here, and what happens is, right, now I've formed the conjugate acid, so NH2H, right? So this is just the neutral form of this of the amide, right? So the amine, right? So this is going to abstract a proton from this guy and form another base, okay? There's plenty of bases around, but I have these free protons that I can abstract because this is much more basic than this is, right? So this hydrogen is going to be able to be abstracted by this negative charge right here. Okay, so now I'm going to get the neutral form of this double bond structure guy. Okay, so now I have this, right? And so what's going to happen is I have another NH2 that comes. All right, and this could happen because my conditions are so extreme, right, that I can keep abstracting these protons, and I can keep resonating these bonds around, right? So I can keep moving it. And NH2, the same thing can happen to KOH. KOH can also rearrange, right? Obviously, we can move from the edge to the middle. These things can both happen in both conditions. But we're going to see why specifically that NH2 favors the terminal one and how it favors it over the KOH. So we said it has to do with it being a stronger base, right? So what this is going to do, it's going to take another one of these protons and it's going to put it right there, all right? So I'm going to copy this again, right? Right, and then what happens is this is going to resonate in and this is going to resonate out again. So what we get, all right, let's look at it. All right, so this is what I get, and then the negative charge is going to be right here, okay? So I have a negative charge on this carbon over here, and this is going to do the same thing, right? It's going to protonate from the NH3. Sorry, I'm running out of space, but okay, so this is going to protonate, and we're going to get what we want. We're going to get where we want. We're going to get the terminal one. So I'm going to paste this again, and it's going to be neutral now. So this is the one that we're going to get. So I'm going to put this in red. All right, but how do I keep this from going in the opposite direction? How do I? Because all that initiated this was the first hydrogen right here, this guy, being abstracted and initiating this negative charge and forming this double bond, and then another one taking off and forming the triple bond, and it essentially moved over, right? And essentially we kept moving negative charges over here. Those kept getting replaced by hydrogens, so hydrogens were taking these negative charges away, right? And then I got this. But how do I prevent this from, let's say I had a hydrogen over here, and how do I prevent this from going backwards? How to prevent this from going backwards? And again, shifting backwards towards the middle. So the reason why this shifts backwards, that doesn't shift backwards when you're in NH2, and why we form the terminal, is because at the end, right, we said we formed the terminal one. So at the end, right, we have one more hydrogen, right? At the edge over here, I had 3 hydrogens initially. There's 3 hydrogens. Remember that? So it was a terminal carbon, had 3 hydrogens. We used 2 to form the triple bond, right? 2 were used up. So now I have 1 left, and this is the protonated version of the acetylide, right? This is what we have right now. And guess what I'm using? I'm using NH2. So because NH2 is strong enough of a base to abstract this terminal hydrogen on this terminal alkyne, we're going to go a step further, and what we're going to get is that it's not gonna stop, right? The reaction is not gonna stop. So I'm just gonna put this over this other one. The reaction is not gonna stop, and I'm going to form the negative charge right here, right? So it's going to abstract this final proton immediately. Once it reaches this position, it's still strong enough to abstract it. So now I'm going to form this negative charge, and because I formed that negative charge there, I prevent it from going backwards now. So I can no longer go backwards. Right, I have this fixed negative charge on the edge of this alkyne, and so when I do that, I'm essentially, you don't have to really know this, but this is the reason why it continues to form this as the major product, is because essentially I am taking out of the equilibrium, I'm taking these terminal alkynes out of the equilibrium. So as I'm taking them out of equilibrium, right, as I'm shifting the equilibrium, I'm altering it, right, away from the equilibrium, right, I'm taking them out by forming these negative charges. And so more of the terminal alkynes are going to form to restabilize the equilibrium, and more are going to keep getting deprotonated, and more are going to keep forming until I run out of the substance to make it. So my products are going to shift continually toward the terminal alkyne and the acetylide anion formation until until uh, until I run out of substrate to use. So this is why NH2 will form this terminal one. Essentially, all you need to know is that it's because it's a stronger base and that it can finally abstract this terminal one over here. But otherwise, right, if I'm using KOH, the same things can happen, right? I can move around, I can take a hydrogen off in any direction, right? But the reason why it prefers the internal one is because it's more stable, right? It's the same reason why double bond is more stable when I have more substituents around it. So the KOH is going to shift stability-wise towards the edge, towards the internal side aspect of the molecule, right? So yes, the KOH can at some point may form this, right? I might have some product that is a terminal alkyne, but it's not the major product because it's not the most stable one. So this will likely tend to go backwards and go towards the middle again. So this is essentially how the reaction works, okay? And you just need to know this is favoring the terminal one. And if I have the H3O plus over here, right? Now, this is the tricky thing that you need to understand. So I said, here I showed you what happens if I have NH2 alone. So if NH2 is here alone, right, and no H3O plus second step, I'm going to be forming the negatively charged acetylide anion, right? Terminal acetylide anion. There is no internal acetylide anion, okay? There is only the terminal one that will have this, right? So, if I don't use the H2O plus second step, this is going to be my product. But if I do have the H2O plus, obviously I'm introducing acidic conditions. I'm going to protonate all of these now, and now I'm going to go back and I'm going to get this guy, right? So this happens if I have H2O plus. This happens if I do not. Okay, so very important to understand this. It's not some magical BS that's happening. All right. So important reaction, very useful in explaining some concepts. Now, for the rest of the reactions on this page, they're essentially more of the same thing, right? So on the first reaction page, we learned reactions with double bonds using Br2 and HBr, right? And essentially that's what we have here. Here we have a Br2 reaction, right? And they're using a terminal alkyne, so one side is more substituted than the other. There's a clear difference. And they're using Br2. And essentially what this is going to do, in the first reaction, stereochemistry is not going to be able to be controlled here. So I'm not going to know if I'm going to add the BRs on the same side or on different sides. Okay, so it doesn't really matter. But you can get a mix of these products. And so it's going to do the same thing. It's going to add two bromines to this triple bond. It's going to reduce it back down to a double bond. So bromine over here, and they can be either cis or trans. Easy. And then I have the HBr reaction, which is very similar to the HBr reaction with the double bond, and I add it in mark, right? So the first one, after the one equilibrium, it's going to add a bromine on the more substituted side, right? So this is a terminal alkyne. One side is a carbon group, the other side is a hydrogen group. So it's going to add the bromine on the more substituted side. If I do another equilibrium, aka if I do one reaction with the triple bond, and then I get the equilibrium, aka reaching the most stable product, and the most stable product has formed, and I have all these are formed now, right? This one right here, this guy, right? If I do another reaction, then I'm going to add another bromine on the mark position and another hydrogen on the anti-mark position. So you just need to know that it's just the same thing, just either it can be one equilibrium, two equilibrium, and how much you want to push it back down to. Okay, and then finally, it's just the same thing, except you have a peroxide present, and we know what peroxide does. It forms the anti-mark addition product. Okay, it's nothing too hard. And then we have another H2 PT PD nickel, right, or nickel, right? You can use any one of these three, and it'll take away all the electron dense regions, right? So this will take away the triple bond, and it will saturate, aka keep saying AKA, but it'll saturate the carbons with hydrogen. So every carbon that is not fully octet, it's going to give it octet by saturating with those hydrogens. Saturating just means every carbon in the molecule is has the maximum number of hydrogens. So whether it's CH2 or CH3, essentially, right, or CH, depending on the substitution, if it's primary, tertiary, secondary carbon. But we're going to get rid of the triple bond, and these are going to get, this guy's going to get 2 hydrogens, this guy's going to get 2 hydrogens. So you see that right here. And so that's essentially what that does. So these are memorization, okay? And then on this page, we're going to be learning some more specific reaction additions of hydrogens only. So these 2 reactions right here, they do the same thing. They reduce the triple bond from triple bond to double bond, and we're going to be adding 2 hydrogens in order to do that. So all you need to know is H2PD, right? So can anyone realize that H2PD, right, is very similar to this one right here. So it should make you think I'm adding hydrogens, right? If you forget, it should make you think I'm adding hydrogen. And the one way I remember that it's adding hydrogen in syn is I just remember that it sounds weirder, right? It's the more complicated one. H2PD, BaSO4, quinoline. She's always going to spell this out. So that's going to tell you, right? And another thing that she can write this out as Lin-Lars catalyst. So you need to know that this is called Lin-Lars catalyst. Lin-Lars catalyst. And you need to know to add them in syn. Okay? And then the other one is just NaNH3. Okay? So NaNH3 is going to add them in anti. It does the same thing, just adds the hydrogen anti, and this one in syn. Easy peasy stuff. Now, these next reactions can be a mix of kind of some understanding. You don't need to know the mechanism. So they can be a mix of some understanding, but also some concept. I mean, some memorization. Okay, so some concepts and then some memorization here. So what you need to know is we're going to be oxidizing triple bonds to a slight degree, right? It's not fully oxidation, right? But we're oxidizing, right? And we're looking at 2 different reagents that do unique things, okay? And we're looking at 2 because I have 2 different chemistries for triple bond. So I have the internal, aka it has a carbon on each side, right? So this lower triple bond molecule over here, this alkyne right here, has a carbon on the left, carbon on the right. That's internal. And then this one on the top is a terminal, carbon on the left to the triple bond and a hydrogen to the right of the triple bond. So both of these have unique chemistries. So they're going to be doing different things, just like how we saw that depending on the type of base I'm using, I'm going to form a different one. So everything has a unique chemistry, and therefore it's going to have some uniqueness to it. So the first box over here, they're showing you 2 different types of the chemistry, so terminal and internal. And they're showing you what happens when I react it with HgSO4, H2O, H2SO4. So the same reagent, there's different chemistries right here. And essentially it's showing that regardless of whether it's internal or terminal, right, I'm going to always be forming what we call the ketone. The ketone is a carbonyl formation that has 2 carbon groups on both sides on both sides of the carbonyl. So the carbonyl is this C double bond O structure. Okay, so I should just demonstrate this visually. All right, so let's take a picture of all this. All right, for the moment. All right, so the carbonyl is the C double bond O structure right here. All right, so this is a carbonyl. Now a ketone is when, let's say I have some carbon groups over here, blah blah blah, have some carbons, forget about the hydrogens for now, I have some carbons. This is a ketone. So R groups on both sides of the carbonyl. Now that aldehyde, the next one that we're going to learn about in the next reaction, is essentially if I have an R group or carbon group on one side, and on the other side there is a hydrogen. What you need to know, the difference between these two guys, is that one is more reactive than the other. And I'll tell you right now, and I've taught this before in the previous exam lectures, that the aldehyde is more reactive. Okay, so that's what you need to know about this. Right? Now, let's see. All right. So in this reaction over here, I am taking either a terminal or internal, and I'm reacting with this reagent, and it's always going to give me the ketone, okay? And so for whenever the thing that's specific, right, the thing they have to be careful about is when it's terminal. The terminal, essentially what we're doing is we're going to get rid of the triple bond, and one of these carbons is going to become the carbonyl, okay? So I'm going to add the double bond O right here or right here. Now, depending on our reagent, the next reagent will do a different thing, but depending on our reagent, it's going to do a certain thing. So for HgSO4, I'm going to get rid of the triple bond, and I'm always going to be forming the most substituted carbonyl, right? So if I have a terminal triple bond, it's always going to be the one that has the carbon group attached to it, okay? And so this is carbon 1, this is carbon 2, this is carbon 3, carbon 4. This is a very nice reaction sheet because they show you the colors of the things so you can see what becomes what. So this blue carbon right here becomes a carbonyl, as I've shown. So this is carbon 3. This is carbon 4. And this is 1 and 2. Carbon 4, all that remaining happens, right? I have acid in here. I have H2O. I have all these things that I need to do these reactions. This is just going to become fully saturated, meaning I'm going to add the required amount of hydrogen, so 2 in this case, to fully make this carbon have octet. So this CH is not going to become the carbonyl because I'm using this reagent. This reagent favors the ketone. So this one is going to be the saturated one. Now, if I have an internal triple bond, it doesn't matter which one I choose. Both are equally both form ketones. So here I have, depending on what you like, within your preference, you can have either one of these form that you could write out. If she has 2 boxes, obviously you write out both of them. In the case that this molecule is not symmetric and you have an uneven amount of carbons on one side. So if I form the carbonyl on the red carbon right here, I have 3 carbons on one side, 1 on the other. If I form it on the blue carbon over here, I have 2 carbons on one side, 2 carbons on the other. So 2 unique products that can happen, okay? Both form ketones. Now, that's all you need to know, really, just memorizing it. Now, if I look at this reaction over here, right, it does a similar thing, but it does something else, right? We need to see the difference. So this one, all that's different is whenever I use Cia2BH and H2O2OH, and this is the big hint right here. If you forget on the exam what this does, and you know that it forms a carbonyl, but you can't remember, do I form the ketone? Do I form the aldehyde? You need to remember that this is H2O2, so we have a peroxide. So peroxides are always, think, anti-mark, right? So you can think of this reaction with H2SO4 as mark because it forms the most substituted carbonyl, and you can think of Cia2BH H2O2OH as anti-mark as forming the least substituted carbonyl always. So the least substituted carbonyl has a name, and that name is aldehyde, right? So the aldehyde is going to be on one side, there's a hydrogen. So I can only use this reaction and get a unique product when I'm using a terminal alkyne. So this has to be with terminal. Okay, because terminal, there's different environments, right? And in internal, the environments are essentially the same almost. So this is always going to form the carbonyl on the carbon that has the hydrogen on it. And that's all you need to know. All right, so that's all you need to know for that. So that's partially memorization. You can kind of understand a little bit to help you. The next one is the oxidation of alkynes, and we do this in KMNO4, H2O, neutral, and cold conditions. And the way this is done is, the way you need to remember this as being different is that KMNO4 is a strong oxidizer, right? But we can control how strong it oxidizes things based on the conditions that we introduce. So Sometimes you'll see KMNO4 warm. Sometimes you'll see KMNO4 neutral cold. Sometimes you'll see KMNO4 as basic and cold, or depending. You may have different conditions. So if this condition is going to allow us to oxidize the triple bond to the degree that I'm going to add carbonyls to both carbons now. So now I don't have to make a choice. Every single carbon in the triple bond, this is going to get a carbonyl, this is going to get a carbonyl, right? This is going to get a carbonyl, this is going to get a carbonyl. But the difference is when I have this hydrogen over here, this hydrogen bond is going to get oxidized. So in the case of terminal always forms something like this, right? So vicinal carbonyls. Vicinal just means one from each other, right? But if I have the terminal alkyne, this hydrogen is going to become an OH. So one is going to be the carbonyl, right? And the other one is going to be a carboxylic acid. That's all you need to know. All right. So for the rest of these reactions, these top three right here, so let's look at these. They're very similar to things we've seen before. So before we've seen reactions with KMNO4, H2O2, OH, and heat. We've seen ozonolysis, O3, and H2O. And essentially, for alkynes, it's different. For alkynes, these two reactions make the same product, whereas before, with double bonds, they made different products. So make sure you review the double bond ones, you know the difference. But for alkynes, they always make a carboxylic acid. So regardless of whether it's terminal or internal, you're always going to have a carboxylic acid. Now, if it's the terminal one, though, this becomes essentially two OH groups, and it gets degraded into H2O and CO2. Okay, and ozonolysis makes the same products, same exact products. So nothing really hard or difficult, just knowing that for triple bonds we have more oxidation essentially happening compared to double bonds. Now here's the one of the most important reactions out of this whole entire unit, okay, this whole entire exam, and she's going to use this over and over and over and over and over and over again. If you're in Orgo Lab, you should have done this experiment already. But if you have not, then it's not a really big deal. It's a very important reaction that we need to understand. And so this reaction has to do with the formation of what we call the Grignard reagent. Now the Grignard reagent is essentially it doubles as both a very strong nucleophile. We usually use it as a nucleophile, but it's also a strong base. Right, and what the Grignard reagent is that when I react any bromine, so it can be a bromine on a double bond, it can be a bromine on a primary, a secondary, a tertiary, it can be any of these things. And what it forms is, so if I have this, let me draw something nicer. Okay, so if I have, let's say I have this molecule, okay, and let's say I reacted this with Mg and ether, okay, and ether, okay, forget the ether part, alright, can't. And this would essentially make, okay, so this would essentially make this, right, so what happens is the Mg is going to, and this is not a covalent bond right here. Okay, this is an ionic interaction. I just didn't have a way to write, show ionic. So it's Mg plus and Br minus. Okay, there's a positive charge over here, and negative charge over here. And what this does is it allows essentially to kind of separate the electrons from bromine and the carbon. Okay, so what I want everyone to think of this as essentially is kind of removing the electrons from bromine and giving it to the carbon that the bromine is attached to. So what we're really doing is this carbon right here is this carbon right here, and what I've just made is now essentially a carbon minus. So this Mg in ether allows us to do this MgBr that forms, but really what it is, it's a carbanion, and it has a carbon with a negative charge on it. And then I just have this MgBr that's here. That's kind of just dissociating the electrons between the bromine and the carbon and really giving it to the carbon. So this is what I'm using to attack here. Okay. And so I can make this with any bromine, any chain that has a bromine on it. Okay. And another version of this is the organolithium reagent. So it does the same thing. We have this lithium that replaces the bromine, and essentially it's the same thing where I have this group with a pair of electrons and a negative charge. So it's the same thing. This is just actually stronger. So this is much stronger. Organolithium is much stronger. Okay. And now, just like any nucleophile, we can use it in a variety of ways. All right. So what we do this a lot with is we react these as a form of reduction, right? So reducing means I'm taking away oxygen bonds. So oxidizing means going from, for example, an alcohol to a carbonyl. That's oxidation. Reduction is going from a carbonyl to an alcohol. Okay, so I can use these essentially in a nucleophilic manner. And if I have a carbonyl, and we said that the carbonyl carbon is an electrophilic site. And if I form the Grignard reagent, so an R group with a negative charge on it, essentially, this is going to act nucleophilically if there isn't an acidic environment around, and it's going to attack the electrophilic site on the carbonyl and push this up. So what I'm going to get from this reaction is O minus this and the new R group that was attached. So that's essentially what we're learning how to do here. We're learning how to attach any R group, just as long as it has the bromine on it and we're able to make a Grignard reagent from it. I can attach any R group. Now there are some conditions that we need to understand. So, and there's a reason for this. And if you did the lab, this will help make sense now. So the Grignard is not allowed to be made. It will not be made in the presence of any acidic environment, right? So I cannot have any acidic protons around in the environment. So basically nothing that can hydrogen bond, essentially, right? And I cannot do it if the molecule itself that I'm trying to do this reaction on. So let's design a molecule that will not work. One molecule that will not work is if I have an alcohol. Okay, so if I have an alcohol, all right, this is my little designing software right here. If I have an alcohol, this is not going to work because essentially what we have is I'm going to have this thing will form, right? I'll form a Grignard with this, right? As long as I have the bromine and I have Mg in ether, it'll form the Grignard. But we need to think about reactions as I'm trying to form moles, right? Millions, tons of these molecules. So I'm forming many of these molecules in one test tube. So if I'm forming many of these, right, and I have an acidic group on the same molecule that has a Grignard, what can happen is, and what will happen is, another molecule that's forming will come and attack it. So this guy will essentially attack itself within the test tube. So that's obviously very undesirable because my reagent is going to be attacking itself. I'm going to be reacting before I even get to do whatever it is that I want. So it's going to prevent any reaction from happening, right? If I can't even form the Grignard that I want, it's going to prevent any reaction from happening. So your Grignard reagent cannot have any acidic protons. It cannot be made in the presence of anything that can be acidic. And it cannot have any electrophilic groups on it. So it cannot have a carbonyl on it. It cannot have anything that's receptive to being attacked. So any groups that have that allow any carbonyl-like groups are not going to be allowed on the molecule when I'm forming the Grignard reagent. And so that'll be a concept question that you'll see on the old exams. But essentially, it makes sense because in the lab, what did you guys do for like 15 minutes before you started the reaction? You got those really hot, kind of essentially hair dryers, right? And you were heating the tubes. You were blowing on the tubes, and essentially you're trying to evaporate and get rid of any H2O that obviously not visible, but you're trying to get rid of it, and you're trying to make the environment as non-aqueous as possible, right? H2O is acidic, and it can form HCl plus. It can form these things. So I cannot have my reaction done in the presence of any water, any alcohols, any carbonyls, anything like that. Okay, so that's why you guys did that in the lab, actually. And if you didn't do that right in the lab, you probably got some kind of bad yield, because as you're making the Grignard, it was attacking itself, or it was attacking other things. And the reason why, especially I cannot do this in an aqueous or acidic environment, is that, let's say I'm forming Grignard, right? I'm forming this R minus and I have the MgBr. But let's say I'm not in an anhydrous environment, right? There's hydrogens around that are acidic. And what will happen is, let's say I have an alcohol. As I'm forming this guy is going to come and just take the alcohol. This is much more basic than this O is with its pairs of electrons. And so what I'm going to do is the R group, or the molecule that I wanted to make the Grignard, is now going to have the hydrogen, and it's going to be stable. It's no longer going to be a nucleophile. So, and once it becomes in this state, this thing is so hard to remove this hydrogen again and form this Grignard back from this O minus that forms, that essentially you lose your reagent. You completely lose your reagent. So you destroy your reagent in the process. So that's why if you got bad yield, that's one of the reasons. So we can use this Grignard reagent in a multitude of ways, and we can get to attack carbonyls. All right, so the first step is attacking carbonyls, and then once I attack it and I get the O minus, we introduce acidic environment, right? So H plus, and we protonate. So this will just become H. And we can do it on secondary alcohols, and we get the same thing. So it's just a concept. There's just different degrees of alcohol. So they're all the same thing. They just form different functional groups depending on what's here. So the first one was the formation of a primary alcohol. You had to go back to what we call formaldehyde. Formaldehyde is just a carbonyl, and it has 2 hydrogens. This is extremely reactive and dangerous for us. Okay, obviously because it's a reactive. So this will give you a primary alcohol. If you understand the mechanism, it'll make sense. You don't really need to memorize what I need to form a primary alcohol. You just need to think about it. So this has no carbon groups on it. So whatever attaches over here is obviously going to be primary. If I have 1 carbon group and 1 hydrogen, aka the aldehyde, if I attack with the Grignard, obviously I'm going to have 1 other carbon group, so this is going to be secondary. If I have 2, obviously it's going to be our max, and it's going to be tertiary. Okay? So don't try to be rigid and memorize things, essentially. It won't help you in the end. Okay? And so just understand that this mechanism right here, the Grignard attacks the carbonyl at the carbonyl, pushes up an oxygen, and then the second step we protonate. And that's really all there is to it. Now, that's the most simple form of the reaction, right? So that deals with all these boxes right here, right? Now let's look at some of these more complicated ones that seem super confusing, but they're really not. They're not confusing at all. If you think about it. Okay, so move this over here. So let's look at this. So Grignard and esters, or acid halides. So what is an ester, first of all? An ester is essentially, I have an R group on one side of the carbonyl, and on the other side of the carbonyl, I have an OR group. Okay? So as an oxygen, it has its own R group. Okay? An acid chloride is an R group, a carbonyl, and chlorine, right? So an acid halide. This could be either bromine or other things. Usually it's bromine or chlorine. Those are the best that we usually use. And so these are 2 things that we need to look at, how this changes what we're doing, right? So for the first reaction, this person who made this is trying to make this confusing. Like they're trying to show something that looks very complicated, but it's really not. And so you'll look at these benzene rings, right? And you'll be like, what the hell is going on? Like, how do I have 3 of them now? I only had 1. And essentially, I want you to forget about the benzene ring. It's just an R group. It's just a fancy R group, okay? Just to make this look more complicated than it is. So it has nothing to contribute at all with this reaction, right? That you need to understand, okay? It does have something that it does, but you don't need to understand it. So let's just think of a regular R group. Okay, let's look at this, and let's say I reacted this with, so we have a Grignard that she's making you use. So let's say I reacted this with something called R prime, so just another unique R group, but it was a Grignard. So R MgBr, and essentially we have, this is the negative part, right? So this is just kind of a spectator, right? So you don't need to think about it. Since we have this R minus. And so what you can do, right, what we understand is that this guy is going to come and attack with its electrons, and I'm going to push this up, right? So I'm going to have R, going to have the O minus now, right? I'm going to have the OR group, and I'm going to have the R prime group that we just added this guy. So what happens is, now you might think, well, now it's time to protonate. Now it's time to form the alcohol, right? No, the answer is actually not that. And so what happens is the molecule favors forming the carbonyl again because it's more stable, right? And so the molecule favors doing internally stabilizing itself, right? And forming a leaving group. So what happens is, so we have all these electron pairs. What happens is this comes back down, right? But you might say, wait, this carbon right here is fully octet. How can I come back down? So that's where the leaving group comes in. So over here I have an OR group. The oxygen over here is already pulling on the sigma bond because it's electronegative. So this is going to come off, and it's going to kick off the R group because it's already a weaker bond right here. So what happens is I get my R, this group, I have my carbonyl that reformed right here, and then I have my R prime, right, that I used in the beginning as a Grignard. And I get an OR minus that I just kicked off. So I formed this group, and this guy was removed. And so now, because I reformed the carbonyl, my Grignard, so my R prime MgBr is still around, and this is going to come back and attack again. And so now I have this, I have the O minus is reformed, I have the R prime, and I have another R prime. Okay? And now, because there's nothing else I can do to internally stabilize this molecule, now I go to my second step, step 2, and I increase the acidity, right? Or I decrease the pH. And this is just going to protonate our molecule, right? So it's going to get rid of the O minus and replace it and protonate it. R prime right there, and R prime. Okay? And so does this look like what we have over here? So over here I have this structure, right? So this was the original ring. So let's say that this is ring number 1. And then the Grignard had a ring of its own. Sorry, I drew all over it. But the Grignard, let's see if I can copy and paste actually. Okay, so the Grignard had a ring of its own. So the first time, imagine this is my R prime. And so the first time I added 1, and then I kicked off this group right here. And then the second time, once the carbonyl reformed, I added another one. So that's where the second and third rings come from. This is ring number 1, this is ring number 2, and then another one comes, and that's number 3. So you see how this works? It's nothing complicated at all. And the beauty of this is you can take this concept, and if you think about it, it works the same way with any other type of leaving group. So OR is just one type of leaving group, right? Obviously, we have other types of leaving groups. So one of those of which is if I have an acid chloride, right? And the same thing happens. When I attach the first one and I get this O minus, and I have the chlorine over here, and I have the R prime that I add. This is a good leaving group. Chlorines are a good leaving group. They're stable when they're negative. So this can come back down with its pairs of electrons and kick off the chlorine or the bromine or whatever. And that's the concept, okay? So that's the concept here. So this is why this can have multiple attachments. So as long as I can reform the carbonyl, I will do the reaction again. So nothing too, magical about this or confusing, and it can be understood if you just put some thinking into it. Now, the next reaction that we have is opening epoxides. So we've learned two reactions to open epoxides. We've learned to open them in acidic and basic environments. Now, we're going to learn how to open them in the presence of the Grignard. So I have my epoxide, right? And if you guys were to say, is the Grignard more basic or is it acidic? And I'll let you think about that for a second. Okay? But it's basic, right? It's basic. So this is going to what you should think is, this is, if you understood the previous ones that I've taught, you should understand this. So this should make you think that I am going to attack on the least substituted side, like in SN2, just like the OH would in a basic environment if I was opening this. And I'm going to attack on the least substituted side, and I'm going to open the epoxide. And so now I have this bond right here. It had one group, right? So this, I have 1, 2, 3. 1, 2, 3. Okay. The oxygen broke off and it went on, it stayed attached to carbon 2. So I have this O minus now. And in carbon 1, I broke the epoxide by attacking this carbon with the strong nucleophile, the Grignard. And now I'm going to have attached to carbon 1, I'm going to have my Grignard attached, so my R group. And so now all we do is we protonate in this next step, and I just get my protonated version. Okay? And that's it. That's it. So opening epoxides using Grignards. Nothing complicated whatsoever. It's just the same thing as opening epoxides in a basic environment. And this is a basic environment, aka a strongly nucleophilic environment. And that's all we do. Okay? So the other reactions are just kind of a little bit, you have to memorize them. So there's two more here for the Grignard. This is just D2O, and it's just showing you how they add deuterium to things. So this is just good to know, it says. I've never seen this come up, but deuterium is just the isotope of hydrogen. And so let's say you have the deuterium D2O, so you had an oxygen with 2 of these isotopes on it. And if we wanted to attach it to a molecule, we would essentially just introduce a Grignard, and I would get this coming and taking these like they were hydrogens, right? It's the same thing as hydrogens, and I would have a deuterium attached to a carbon group that I wanted. So that's just how they would do that. And then the other one is called the Quarry house reaction. I've never really seen this. It's not really important as far as I've seen for Orgo 1. But if I would do this last. If you're having, like, you're struggling so much with reactions that you couldn't memorize these, I would memorize this one last. It's one of the lowest priority things you need to know, but it's just another way to attach carbon. So this is your CH3 group, the Br. You use lithium, so you use organolithium reaction. Then it becomes CH3Li, so this becomes essentially kind of like the Grignard, almost the same. And then you do this CUI step that makes this CH3 2, and then the CuLi. And then let's say you add anything that has an R group of the bromine, and essentially this would attack like SN2 or SN2 essentially. So I would attach one of these CH3 2 groups. So it's just a way to attach the CH3. It's very strange, very weird, but it's just one of these random reaction sequences that you have to, I guess, memorize. Just be familiar with this, okay? And now we're almost done. We're almost done, okay? I think I'll end the video now, and I'll continue with these remaining last 2.5 pages in the next video. All right? Best of luck and study hard.